Okay, hi. This is our last project video for EE 301. As you guys may already know, we made an AlphaLIDAR, a LiDAR project, and here what it is. You can see the structure here. We designed a structure in order to prevent against any interference that might occur due to the externalities. And then we have the oscilloscope here. As you can see, this is the LEDs waveform, and this is the photodiode. Since we have no object in front of it, it shows 0, obviously. What we will do today is we want to show you that our structure is indeed working and how we measure the distance by using the speed of light. So before actually going deep in that, we set the distances here actually. So this was 40 centimeters. I don't know, maybe you cannot see it, but it says 40 centimeters. We measured it. Here it's 20 centimeters, and then here it's obviously 0 centimeters. So we will first measure the 0 centimeters in order to extract the impulse rise and fall time, and then measure the 20 and 40, and we will see how it can be seen on the oscilloscope as well. So let's start with the 0 centim. Okay, now if ZEC1 places the mirror in front of the LED, which is 0 centimeters away from it, we can see a nice plot like this. Its voltage is changing as ZEC1 changes the mirror's direction. So now we will zoom in to the waveforms and try to find the distance between these two plots. Here, the waveform for the LED is decreasing, it's slow, and it starts to rise for the photodiode. Since photodiode generates a reverse current, we see such a graph. It was really confusing at the first place, but since we understood it later, it became really clear. So now we will stop the video and we will zoom into this region and show you guys how the measurement is being done. Okay, after long hours of adjustment, we made it as follows. What we made is we zoomed in the decreasing, the fall and the rise edge of the diode. As you can see, the diode is rising, but we don't care about this point. We want to observe this point, how it changes. So let me zoom in a little bit more. So we will put a cursor here, and I will set it to track. So for the cursor, sorry, it should have been cursor. Okay, channel 1. So for the cursor 1, I'm gonna assign it to channel 1, which is here. When the LED goes down, I set it that point, and for the diode's cursor, okay, it's here, we will see the time difference between them. So when we actually, it's really interesting, set it to the most bottom part, the global minimum part, it is the time when the photodiode sees our light beams that is coming from our LED, and it starts responding to our LED. So which is around actually here 760 or 800 nanoseconds, and that's what actually we measured previously on the other oscilloscope. So what I will do is I will just note this 800 nanoseconds down here for the 0 centimeters, and this is the time that constitutes our or this is the time that we will be using throughout these measurements, because this is our reference point. This is our characterization point. Normally, one might expect to obtain higher, or lower results, since the photodiode has a fall and rise time of 100 nanoseconds. But since this is not ideal, we observed this plot. And now we will set our object to 20 centimeters, and we will see what we'll be seeing on the oscilloscope and try to find the distance between them by measuring the time of flight. Okay, here's now the object is apart from the diode, and they have a 20 centimeters around distance between them. So what do we need to actually see from here is we need to see 40 centimeters, right? Because the light is going out from the LED and it hits on the mirror, on the object, and it reflects back to the diode. So 20 plus 20, which is 40. And now I'm really curious whether we can see 40 centimeters here or not. Let's see. So again, we will try to make the adjustments, but since it will take so much time, we will pause it. Also, let me remind something here, which is very important. Yesterday, once we were making the measurements, we used a different oscilloscope, as you may see on our report on the images. That's because we used Ozyegin oscilloscope. It was really, high precious, actually, better than this one. So that's the reason behind it. Let me be clear. Yeah, we can pause it and we can see what will be happening. Okay, now we zoomed in the waveforms. Again, this is the LEDs and this is the photodiode's response. So what we want to do is now, let me zoom in a little bit more. So this is actually the time that we are seeking for, because after this point, as you can see, the diode is increasing, right? It increases, but up until this point, its response time, it depends on the distance, etc., and that will give us the distance measurement. So what we will do is, again, we will put a cursor track, cursor A, and I will again set my cursor A to the hinge of the LED, and here, well, it's not really certain, but so this is the the global minimum point. So I'm just gonna place it here by inspection, and I guess it will be around like 800. Okay, how much? I think, yeah, this is the global minimum. It will be like 920. So let's see whether the calculations is correct or not. Well, we don't see that much precision, as you may have already read in our reports, but we will see. So 920 minus 800 is 120 nanoseconds between them. 100 nanoseconds times 10 to the minus 9, which is now in seconds. Okay, we multiply it by the speed of light, and which gives us a 35.9 centimeters. If we divide it by 2, because this is the distance doubled, as I explained, it's gonna be 17.98 centimeters. Well, which is really close to 20 actually, which is really impressive. And now we will go with the 40 centimeters. Okay, now it's 40 centimeters apart from the photodiode, and we will inspect it from the oscilloscope whether we have a coherent results as we have seen with the 20 centimeters. Now we will pause the video again and we will continue it once we zoomed in. Okay, so we zoomed in the oscilloscope. What we will measure here is, as you can see, there is a peak. It's increasing after this point. We want to measure the time distance between here and here. So let me zoom in actually a little bit to see it better. Let's use the cursor again, track. So we don't expect perfect results, as you already see in our report, but just to show you. So let me set it to the min point here. Okay, now this is at its mean. Let me adjust this point further. Okay. So I think now it's in the minimum point. It's around 100 microseconds or maybe 990, I don't know. So which is 1000 nanofarads. So let's see if this is correct. 1000 nanoseconds minus 800, which is 200 nanoseconds times 10 to the minus 9 is equal to this number. And I will multiply this number with the speed of light, 729,458, which is 59.65, 59 centimeters divided by 2. It's 29.97 centimeters. Well, it should have been 40, but we are off by 10 centimeters. But yeah, I think that's, normal or as expected. So that's how actually the distance measurement works. We literally put an object here with the desired centimeters or desired distance between them, and we try to see the time difference, the time of flight, while looking at the oscilloscope. The oscilloscope precision matters the most, because if you use a high precision oscilloscope, you can come up with really good results, and you can use other mathematical techniques like derivatives or second derivatives, and with the derivatives you can literally find the minimum points or the minimum or maximum rate of change, etc. But yeah, this is how the AlphaLIDAR works. Thanks for watching our project video, and yeah, see you later. Bye bye.
Thank you.